Okay, good morning, and we'll continue in a way replacing yesterday's lecture. So I think the first thing I need to do is essentially go through the formula that was actually not really explained well in the last lecture. So let me just open up this whiteboard. I will share the screen. Okay. So let's look at the lecture notes that we had. This one, the other one. So I think I have a bit of explanation to do for this formula. Yeah, this part sort of fumble a little bit. I've forgotten how to think about it. So the question is what actually happens over here. One really have to consider what is this particular state. Okay, so one should be looking at the following. Let me just recall what EZ is. That EZ should be an eigenstate of your LZ. Okay, so let me go to the whiteboard. So recall that LZLM is going to be MH bar LM. So if one takes the so-called the unit vector, so this is a position eigenbasis kind of thing. So this will become MH bar YLM. Okay. So if one restrict to the state EZ, so let me just think of how to explain this. So well, okay, so one worries what is this, let me just go back to the equation. Why is this LMEZ is going to be having this Kronecker delta thing? So really it's coming from this equation over here. So this is, in general, you have a function here, but EZ is essentially MH bar YLM 0 phi, okay, because essentially this is already in the direction of Z, and then if you remember spherical polar coordinates, so Z, X, your this is phi, this is theta, oops, theta here. So when theta equals 0, it's already projecting on the what we call z direction. Now there are two ways of thinking about this. The first way is to say that okay, one could not have. If you remember, this should be equals to. Let me go back to this. I can't remember precisely. Your spherical harmonics is given here. What it is, I think it should be somewhere above. Yeah. Okay, we have this PLM cos theta exponential Im phi. So let me just go back to the whiteboard. So I should be having mh bar PL cos theta is actually just 1 and Eim phi, but one should be really thinking of this as just like a scalar, and there should be no function of phi involved. So in other words, in order for this to what you call, in order to this to be well defined, for this quantity to be well defined, this cannot be there. Okay, so in other words, if this is there, it will have to be a function of phi. Okay, so in this particular case, then the only way that this dependence on phi can vanish is you have m equals to 0. Okay, so that's one way of thinking about it. So making your quantity here is actually to be well defined. Okay, but another way of thinking about this is essentially just to go back to Cartesian coordinates. Push this thing up. Recall that Lz is simply this what we call in Cartesian coordinates x d dy minus y d dx, if I'm not mistaken. Check. Yeah. So it's actually equals to that. But then what happens in this particular case is that if I were to add this on, say, Ez, oops, let's say this is going to be on Ez kind of thing, then oops, not thinking properly today. X d dy minus y d dx, and if I really want to put this on a position basis, this will be y l m well, okay, let me put the theta phi first, but this function, because it's now in the z direction, okay, this should not depend, will be independent of x and y. Okay, So in other words, when it differentiate with respect to y, it should get 0. When it differentiate with respect to x, okay, it should be 0, because the only direction, the dependence on the direction should be only in z direction. So that is why, in other words, this will be equal to 0, and that means that implies that m equals 0. Okay, so there are two ways of thinking about this quantity of the one that you find in the notes. Okay, so in other words, here essentially this is coming from that argument. Okay, so I hope that settles the previous fumble in some sense, and I think the rest is just the normal thing that I mentioned earlier. Okay, so the Wigner functions are just going to be used mostly in studies of spectroscopy. So, and then when you do addition or angular momentum, this kind of quantity will be of importance. So the next thing that we wanted to do is essentially to look at the theory of addition of angular momentum. So let's go back to the beginning. So before we go to the general theory, I think we'll try to do the simplest case so that you can actually see what's going on. Okay, so the simplest case of addition or angular momentum is the addition of two spins. Okay, so in other words, what one should have in this particular case is to consider a composite system of two spin half. So this two spin half are essentially independent of each other. Okay, so in other words, what we'll have, the addition of two spins is really addition of this spin operator on one Hilbert space, and then the other will be acted upon by an identity operator. Okay, and then this one will be identity operator on the first Hilbert space, and then the S2 is acting on the second Hilbert space. So in other words, one should really think about having Hilbert space being spanned by two spin. So this is going to be S1 and then M1 tensor product S2 M2 kind of thing. Okay, so this will be the basis of the composite system of two spin half. Spin halves. So in other words, in this particular case, this, for example, will only act non-trivially on that, okay, and the identity will act trivially on that, okay. And for the second one, the identity will act trivially on this, and then it will, the other one, the other S2 here is going to act non-trivially on that. So that is how we think about the addition or angular momentum. So really, when it's written in this way, it's really a shortcut for this notation. Okay. So, and we also require that they are independent of each other. That means we require them to be they are spin operators for each independent spin to commute each other. Okay, so otherwise that would if this is not 0, that means it's not independent, or there must be some kind of interaction between the two spins, which we will not consider at this point in time. Okay, so, and as I said just now, that the basis of the composite system can be now written in this way. Okay, so why we have actually we are ignoring this S1 and S2 because S1 and S2 is fixed to equals to a half. Okay, so we can emit this label, okay, and then just label it by M1 or M2, which is now written as epsilon 1 and epsilon 2, where epsilon 1 and epsilon 2 can be a plus minus kind of a state. Okay, okay, remember that your plus and minus here is corresponding to SZ plus or minus H bar on 2 plus or minus. Okay, so really this plus or minus is actually referring to the individual Z component. Okay, so you have epsilon 1 and epsilon 2. We have to also remember that the fact that the individual spin, say for spin, the first spin, we have the angular momentum algebra, okay, from the commutators, okay, and similarly for your case of your second spin, okay. So in general, one should expect if the total spin, okay, if this total spin is supposed to behave like an angular momentum, then you would also expect the total spin operators, so without the subscript 1 or 2 here, this corresponds to the total spin operator component I, and this total spin component J, and they should behave like an angular momentum algebra. So that means commutator of Si and Sj should give you I bar epsilon ijk as key. Okay, but really what is the total spin? You have to remember the total spin is coming from these operators. Okay, so one has to also look at, just like the case of your S, say Si, for example, or maybe I should just drop that at the moment. How should I say this? You recall that all your angular momentum states are going to be of this form, okay, where this corresponds to your J squared, right? So J squared, oops, everything's gone. Jm, so the labeling here, your J corresponds to your J squared Jm equals to Jj plus 1 H bar squared times Jm. Okay, it's the total angular momentum squared. So if one needs another label for the total spin, one should also form this S squared. And S squared can be thought of as follows. You can think of this like this is just like another vector of the total spin, dotted product, dot product with this total spin as a vector. Okay. But then you also have the fact that your S is given by S1 tensor product 1 plus S, plus it's not very friendly, but okay, S1 tensor product 1 plus 1 tensor product S2. Okay, so if I have S dot S, I have to dot product this whole thing. Okay, so I will have S1 tensor product 1, 1 tensor product S2 dot with S1 tensor product 1 plus 1 tensor product S2. And this dot product is for the vectors. Okay, so if I take this term with this term, then I'll get my S1 squared. So this is really what? This is really S1 squared tensor product 1. Okay, and then the other term will be this with that. Okay, this with that will have S2 squared, which is really 1 tensor product S2 squared. Okay, and then we have the cross term. So this one dot with that. Okay, remember the dot is you just taking the components here. So this will be S1x, S1y, S1z, dotted with S2x, S2y, S2z. Okay, so and that is in terms of vectors, but you have to think in terms of the operators themselves, which one multiplies which. So this, for example, will multiply with the identity. Okay, and this identity will multiply with S2. So in other words, what you're going to have in that particular case is something like S1x tensor product 1 multiplied by 1 tensor product S1x, S2x, sorry. And then plus, okay, because the dot product, and then I have S1y tensor product 1 times 1 tensor product S2y. And then another one will be S1z tensor product 1 and 1 tensor product S2z. And this is just simply S1. So if I take this S1x, multiply this identity operator, that will just give you S1x, and then the identity operator x on this S2x, that will just give you S2x. Okay, so similarly for the rest. Okay, and that is this one multiplies that term. We also have the other term, 1 cross S2 times S1 cross 1. Well, you can do this for yourself. It will give you the same operators. So, and these operators, you can make a short hand notation, just like a dot product thing. So this is really S1, S1 dot S2. Okay. So the factor of 2 is coming from the two what you call the two different products of the mixed terms, of the cross term. Okay. And so that will be your S squared, and one should also have the SZ. So the SZ will be coming from S1Z tensor product 1 plus 1 tensor product S2Z. Okay. So I hope this notation, because you have to think in terms of the Hilbert spaces, there are two different bases, okay, tensor product with each other. So the operators follow how the Hilbert space is essentially represented. So in this case, there will be a tensor product, even with the operators. Okay, but sometimes we don't write. If you see most of the books, they don't write everything in full. So one has to understand this. This is done sort of implicitly. Okay. So generally, one can summarize this, that your total spin now has this kind of eigenstate Sm, okay, with this what you call eigenvalue for your total spin magnitude squared given by S plus 1 h bar squared times Sm, and Sz times Sm is just your mh bar Sm. Okay, so the only thing that we need to find out is what really is this capital S and capital M here. So the only trivial thing that one should maybe I should do this in whiteboard. The only definite thing that one could actually see is coming from the Z component, because the total spin squared is a bit more complicated. So we just look at S1Z, sorry, SZ. SZ equals to S1Z tensor product identity plus identity tensor product S2Z, and this has to act on so acting on states like S1 M1 tensor product S2 M2. Okay, so if I just think about this, for example, so I'm going to shorthand notation this, because S1 and S2 is just half, so this is M1 M2, or your epsilon 1 epsilon 2, which is correspond to plus or minus, this will be plus or minus a half, plus or minus a half. Okay, so if I do that, then I'll see the following. Just do epsilon 1 epsilon 2 here. This should be epsilon 1 h bar on 2 I hope you can see this, epsilon 2, and this is, sorry, this is epsilon Z, epsilon 1 epsilon 2 is going to be epsilon 2 h bar on 2 epsilon 1 epsilon 2. Okay, if you get confused for some reason or another, okay, go back to this notation. Okay, and then you can see that, okay, this one acts on that, okay, and it will give out this eigenvalue m1 h bar on 2, sorry, m1 h bar, sorry, m1 h bar, and then the identity will act on that, and that doesn't do anything, so you get your m1 h bar just being a number outside, multiplying this back again. Okay, similarly for this, you see that, okay, this will multiply that, it doesn't do anything, but this multiplies that, will give you m2 h bar. Okay, so most of the time we'll try to simplify this so that you just do this implicitly in some sense, and then you get all this notation. So now what do we have? So essentially Sz acting on epsilon 1 epsilon 2 must be equals to h bar on 2 epsilon 1 plus epsilon 2. But we also have the other notation that oops, what do we do? No, I don't want to do that. Okay, I just want to put it Okay. So the other notation that we had was to define this just like your total spin acting like a angular momentum state. So I have Sm and Sz acting on this Sm should give you m h bar epsilon 1. Oh, sorry, Sm. Okay. So we have two different descriptions here. So and these two different descriptions should coincide somehow. So the rule is that when you do this, your eigenstate for Sz, they should sum up in the same way. Okay, maybe I do this first so that you can actually see. So I have this description coming from the total spin. Okay, and the total spin, my claim is that you can have a total spin of 1. And if you have a total spin of 1, the component, the Z component will have either m equals to 1, m equals 0, and m equals to minus 1. Okay? But the other possibility is to have your total spin to be 0. Now I'll explain why this has to be there. Okay? Total spin to be 0 in a way that your m, the only way that can be correspond to total spin 0 is that your m is also 0. Okay, so this is coming from the total spin description, and then you also have the individual spin, which is coming from spin 1 and spin 2. So spin 1 and spin 2 will have your Z components m1, m2. Okay, and this can correspond to a plus plus. Okay, spin up, okay, and then spin up, spin down, and spin down, spin up, spin spin down, and spin down. Can you hear that? You guys there? I have to check. Okay. So you can hear surat khabar lama dah. Okay. So so you have two different descriptions that should somehow coincide. So the only way that this can coincide is the following way. Okay. Your spin up here, okay, must correspond to the highest state. Okay, so the claim is going to be the spin up state will correspond to total spin equals to 1, and the Z component is also equals to 1. Okay, and then perhaps I go here first. The spin down state should correspond to total spin 1, and then with the Z component to be minus 1. So that's the easiest. These two are perhaps the most obvious correspondence. Okay. Okay. Because why there's going to be no states which are having both spin up, and then states which are having both spin down, they should correspond to the higher state and then the lower state. But then you have a state in the middle. Okay, the state in the middle is given by a mix-up state between spin up and spin down, and it has to be a superposition in this form. Okay. Now this superposition in this form, having with the plus sign, you have to think that, okay, there is a possibility to have a minus sign instead. and that gives you this other combination which correspond to this spin, total spin 0, and then your m is actually equals 0. Now this is just claim without any proof. Now we're going to prove this. Okay. So how do you actually do this? So the relation here, the most obvious relation here is this m equals to m1 plus m2. This is from the total spin, this is from the individual spin. So you can think of, for example, the one state, okay, corresponding to this, will have m equals to 1, which is equals to half plus a half, okay, which is m1 m plus m2. Okay, and similarly for 1 minus 1, so m equals to minus 1, and this will be minus a half plus minus a half, which is the m1 and m2. Okay, for 0, you can see that m equals 0 will come from half plus minus a half, or minus a half plus a half. It doesn't matter in this particular case. So that's why you have the two different combination over here, plus minus or minus plus. Okay. The only sort of mystery in some sense is why is this thing should be here. But if one really thinks what's happening, if you look at the number of states that you're supposed to have, okay, this is from the individual spins, and this is pretty obvious because we have seen how this eigenstates been constructed from the individual spins. So there are 4 of them. So the composite Hilbert space will have 4 bases. Okay, so in other words, the total spin, which also describe the composite Hilbert space, should also have the 4 bases. So if we limit ourselves to s equals to 1, we will only have 3. So we'll be missing 1. Okay, this 0, 0 thing. So that's why you have that 0, 0 in some sense, but we need to really explain how to do this, and this is using what we call the ladder operators. Okay, you remember ladder operators? Let me see. I think I have my old notes somewhere. Not sure which lecture is this, 26. Yeah, okay, good. So let's see that. Okay, if you remember, how does the step up and step down operators act? Somewhere. Is it? Oh, here, okay. So this is how your step up operator or step down operator acts on the angular momentums. Your lambda here is really j plus 1. Okay. So here is jm essentially. So this is okay. Maybe I should write lambda equals to j. Oh, never mind. I mean, there's a 2 different notation here. So so lambda is actually your j, so you can represent your lambda by j here, but the total angular momentous should have this jj plus 1 h bar squared kind of eigenvalue. Okay, so the way it acts is essentially that. So this maybe I should write as j plus 1 if I'm not mistaken. Let me, I hope I'm right. I can't precisely remember now. Yeah, I think probably that's it. Read this now. Okay, so this will be minus m plus or minus 1. Okay. H bar. Okay. So all you need to do now is to use this formula for the total spin as well as the individual spin. Okay. So let me get back to lecture 3 here. So the claim is this ladder operator for step up ladder operator should corresponding to the individual spin step up ladder operator in this way. Okay. So you have your S plus given by S1 plus S2 plus, and S minus is going to be S1 minus plus S2 minus. Remembering that you actually have this thing, okay, for that. So now one can start doing this and see that what we claimed earlier about the correspondence between the states should be what you call should follow from this kind of operator kind of definition here. Okay, so let's look at the 1-1 case. Okay, and remember the 1-1 case is supposed to be equal to the spin up. So here is spin up, here's another spin up. Okay, so I'm writing as your SM here, SM here. Okay, so this one this one will act on that state and try to lower down your M value. Okay, so if you write down the M value here is going to be 1, so you will lower down to 0. But remember, there will be this thing here. Maybe I should rewrite this thing over here. Can I cut and copy this? Let's see if I can cut and copy. So I need this one already. Yeah. Copy. Let's see if I can get this done over here. Oops, not this. No, that's not what I want. What's happening here? Sorry about this. Still playing around with this kind of thing. I'm not sure whether. Well, there's something to. Okay, never mind. Let me just try to remember them and write it down. Okay, so let's look at that. So Jz, J plus or minus Jm. So let me write it down here. J plus or minus Jm should be equals to square root Jj plus 1. And then this is minus and then plus or minus. Okay, minus m plus or minus. I hope this is the right formula. I might be wrong with respect to this, but let's see. Let's hope it's not. So that is m plus or minus 1. So if I have, for example, s plus, no, so I have 1 0, 1 1, sorry, then I should have what? G will be equals to 1. I think I'm going to get it wrong, so probably this is something else. That will be, sorry, that will be 1. No, this is not plus. I want this to be a minus. So let me just, I'm just, okay, 1 1. I'm just worried about this. I might just have something else over there. But let's just try to work it out. 1 1 plus 1 minus 1 1 minus 1. I think it works out. Okay. So that is h bar. And then this is going to be 1. And then this 1 will be lowered down to 0. So this is 0, this is 2. So you have root 2 h bar 1 0. Okay. And then you have the s1 minus, and then this is half half, tensor product half half, and then this will also have s2 minus half half, tensor product half half. Okay, so this will be equals to, again you have to think of this acting only on this, and then there's an identity operator acting on that. So that gives me, let's see, so half plus 1 minus a half minus 1. Is that right? And then this will be a half minus a half, tensor product half. And then the other one would be a similar thing. I hope I'm doing it right. I'm just afraid I have all the factors wrong. So this is half half, tensor product half minus half. So let's work out what this quantity is. This is 3 over 4 minus 104 or plus 104, right? Oh, I've forgotten the h bar as well. H bar. Is that right? 304 minus 104. So that gives me root 2 over 2. Hang on. Well, let me just write. So this is 3 over 4 minus 1 over 4 is root 2 over 4 h bar, and then this is half half minus a half, tensor product half half plus, let me bring this up.
Okay.
Yeah,
Plus 1 over 4.
which one?
a 1 there. 1/2 minus 1 is negative 1/2, right? Then times negative 1/2. Wait. Yeah, sorry.
Is that right? This is 3.
9 gets a 1, right?
Oh, it should be a 1. Yeah. Sorry. So this is going to be a 1. Sorry. Yeah, you're right. So this is 1 H bar half tensor product with half minus a half. Okay. So in other words, this will be H bar times let me put in the plus and minus notation. So this will be minus plus minus. Okay. So now this term should be equal to that term. Okay. So let's just try to write this thing down. So I have this H bar cancel off on both sides. Let me just pull this thing up a little bit more. Okay. Oops. Oh. Let me put down a little bit so that I can remember what it is. Okay. So I have root 2 1 0 equals to minus plus minus. Okay. In other words, bring the root 2 on the other side, so I get 1 over root 2. Spin down, spin up, spin up, spin down. Okay, which is precisely what we had earlier over here, which is this one. Okay, so you can see now this can be done in a more mathematically precise way. Okay, so then you get that. Okay, and if you do it further, okay, add this s minus on this 1 0 state, then I should get 1 minus 1 for the total spin. But then that should now correspond to the spin down state. So I think, I'm not sure whether I work it out over here. Okay, it's an exercise for you. Okay, so you just add your spin down operator on that, and also the spin down operator on the individual spins. Okay, and you should get the identification of 1 minus 1 and minus and minus. Okay, so the only other thing is going to be the 0 state. Okay, the total spin 0 state. So that has to be sort of imposed rather than no, because you don't have your ladder operators only act on your z component in some sense. Okay, so you will lower and raise the z eigenvalue. Okay, so there's no combination, no kind of ladder operator that acts on the total angular momentum. Okay, so that would have to come from some kind of orthogonality combination. Okay, so in other words, we know that two eigenstate with different eigenvalues. Let's say I have eigenstate lambda here, and then I have eigenstate lambda dash here. Okay, then this should be orthogonal. Okay, 0 if lambda is not equals to lambda dash. Okay, so your lambda here correspond to your both your s and m. Okay, So S and M here, for example, S equals 0 state, M equals to 0 state. Okay. This should be orthogonal to S equals to 1 state, M equals to 0 state. Of course, it's orthogonal to the M equals to plus or minus 1. Okay, but the one that's more important for us to look at is this S equals to 1 state, M equals 0 state. Your M is equal, but your S is different. Okay. If you have, for example, M equals to 1 and M equals to minus 1, that is already obvious that it's going to be orthogonal to M equals 0 state. Okay. So now you're actually using this fact to build up the other state that's being left out. Okay. So one can start thinking of this way. So you start doing some kind of linear combination, say alpha plus minus and beta minus plus, because remember also the other fact that we need to have is M equals to M1 plus M2. Okay. So in other words, this 0 has to come from this kind of combination. It cannot come from anything else. So now you just take the orthogonality with 1, 0. So 1, 0, we already know that 1, 0 is essentially this state. 1 on square root 2, plus minus, minus plus, right? So, and then you can make this inner product, and then you'll be able to show that alpha equals to minus beta, and then you require that the 0, 0 state has to be normalized. That means alpha has to be 1 on square root 2. So I'll leave this for you to actually figure out, do the details. Okay. So finally we get this combination of the total spin 0 equals 0, total spin 0 and M equals 0. Okay. And then this corresponds to the other combination of plus minus and minus plus. Okay. So I think I've exhausted to this hour. So I'll stop there for now. And let me get your attendance. There are only 2 of you. Right. Okay. So I hope if there are any questions about that, just let me know, and then or we can discuss at some other point. So I'll stop for today. Okay. Thank you.
Master.
Right. Bye.